For a human to work in space, he or she must have a spacesuit. It protects the astronaut from the vacuum beyond the atmosphere, supplying oxygen as well as insulation from the extremes of heat and cold. The spacesuit has to have means of communication with the outside world, and it must enable freedom of movement. The modern spacesuit is the result of a long and complex evolution. Long before humans had traveled to space, aviators wanted to fly at heights that could not support life. In 1932, Auguste Piccard flew above 16,000 meters in a helium-filled balloon. To stay alive, Piccard ascended in an aluminium pressure vessel fed with compressed air. Spanish aviator Emilio Herreras came up with a different solution. His stratospheric suit never flew. It was an idea ahead of its time. In the United States, aviator Wiley Post had supercharged his plane, the Winnie Mae. It could fly at 15,000 meters, where the jet streams blow. Post knew he could save fuel and fly faster at that height. So with the help of tire maker B.F. Goodrich, he devised the first serviceable pressure suit. At this time, even military aircraft were flying at much lower altitudes, where the use of a simple oxygen mask was enough to ensure pilot efficiency. However, as jet power was introduced, operational ceilings lifted. At high altitudes, low ambient air pressure meant the oxygen mask would lift off the face when oxygen was fed to the pilot at pressures high enough to sustain life. When bombers like the B-36 began long-duration missions at high altitudes, they adopted pressurized crew compartments. Yet the pressure suit, with a fully enclosed helmet, was necessary as sudden cabin depressurization could be lethal. In the 1950s, partial pressure suits became common. They had inflatable capstans that stopped blood draining to the legs under heavy G-forces, avoiding blackouts. Air crews hated them, but figures showed they functioned more effectively when wearing them. In 1955, a unique American spy plane made its first flight. The following year, the U-2 began reconnaissance missions over the Soviet Union. Flying at 21,000 meters, it was beyond the range of Soviet radar, and neither jet fighters nor missiles could reach it. Pilots flying the U-2 wore a new partial pressure suit, the MC-3. Rather than save a pilot's life in case of sudden depressurization, this suit was designed to be under pressure throughout the mission. Without it, the pilot's blood would boil. As missile technology developed, it appeared that human beings would be dispensed with as a weak link, not able to cope with conditions imposed by the technology. But the US Air Force had different ideas. They felt that a pilot could make better decisions than a guidance system, and they began a research program using hypersonic aircraft to learn about the problems associated with ultra-high speed, ultra-high altitude operations. The culmination of this program was represented by the X-15, a rocket-powered aircraft that could fly to the edge of the atmosphere. Because of its limited fuel load, the X-15 was launched from beneath a B-52 bomber at an altitude of 15,000 meters. The cabin of the X-15 was pressurized with nitrogen to reduce the risk of fire. For the pilot, a new full-pressure flight suit, known as the XMC-2, was developed. It too was pressurized with nitrogen. A neck dam excluded the nitrogen from the helmet, which was fed with oxygen for life support. This suit was the predecessor of NASA's most important spacesuits. The X-15 set the speed record for a powered aircraft at well above 7,000 kilometers per hour, and the altitude record at just over 107,000 meters. The first real spacesuit was worn by Russian cosmonaut Yuri Gagarin. In 1961, aboard Vostok 1, he became the first man to orbit the Earth. His suit, the SK-1, was to protect against capsule depressurization and to sustain him during ejection from his craft. The Vostok cosmonauts had to parachute to the ground because their capsules landed too heavily. Since 1959, the newly formed US space agency, NASA, had been working towards launching an American into space. 7 test pilots had been selected as the Mercury program's first group of astronauts. The first attempt would be a short hop. As the only booster available at the time, the Redstone lacked the power to reach orbit. An important part of the preparation involved the development of a spacesuit. As a starting point, NASA looked at the XMC-2 used for X-15 flights and the Navy's aviation pressure suit, the Mark IV. Both were full pressure suits. NASA decided that the Mark IV suit, worn here by Alan Shepard, was lighter and could be more easily modified for spaceflight. The boot leather and the suit's grey outer covering would be replaced by aluminized nylon for greater thermal control, and the helmet's rubber diaphragm surrounding the face was eliminated, with oxygen now entering via a hose at the waist to help cool the suit. For all 6 manned Mercury missions, the Mark IV suit performed well, but the demands placed upon it were modest. Like most pressure suits at the time, it served as a backup in the event of cabin pressure failure. Because this never happened on the Mercury flights, this suit was only ever pressurized at launch. In the early 1960s, the Soviet Union's space program was achieving an impressive list of firsts. For the United States, this was a source of national embarrassment. In 1961, the new president, John Kennedy, had boldly proclaimed that America should land a man on the moon before the end of the decade, and NASA was flooded with funds. This was the beginning of the space race.
I don't think we ought to waste any money, but I think we ought to do the job. And this will be done in the decade of the 60s.
The Mercury program was terminated early, in favor of a more complex series of missions with the aim of solving problems associated with sending a man to the moon. The Gemini program made use of a new 2-man capsule boosted to orbit atop a modified nuclear missile. Gemini required a new suit with new capabilities. NASA now understood future missions would have to last much longer. Suits would have to be more comfortable, and astronauts would have to leave their spacecraft in the vacuum of space. Gemini controllers were planning the first spacewalk. In the less open Soviet Union, they were also preparing for a spacewalk. Cosmonaut Alexei Leonov was practicing with an inflatable canvas airlock in temporary weightlessness in an aircraft in a parabolic flight path. He was wearing a new spacesuit, the Berkut, designed to function outside his Voskhod spacecraft. The airlock was needed because the new Voskhod still did not have solid-state electronics. Its thermionic valves needed air cooling so the capsule could not be evacuated. In March 1965, Alexei Leonov left the airlock on Voskhod 2 to float freely in space. It was another first for the Soviet Union. Soon, his Berkut spacesuit began ballooning to such an extent that Leonov could not reach his camera's shutter release, positioned on his leg. It was not until after the fall of the Soviet Union that the full story became known. The Berkut spacesuit had expanded so much that Leonov could not get back inside. Only by venting his spacesuit could the cosmonaut regain entry to the Voskhod capsule. Back at NASA, they heard that Leonov's spacewalk had been a resounding success, but they felt the Gemini program was catching up. In June 1965, astronauts Jim McDivitt and Ed White were preparing for the world's second spacewalk. Gemini 4's launch went smoothly, and on the third orbit, Ed White left the capsule. Although they didn't know it, the greater sophistication of the Gemini craft made this spacewalk much simpler than Alexei Leonov's just 2 months earlier.
Okay, I'm out.
It was easy to depressurize the entire capsule, so no airlock was needed, and Ed White's spacesuit was fed through an umbilical connected to the spacecraft. Leonov carried his own oxygen in a backpack that made re-entry to the Voskhod capsule that much harder. Within the structure of the Gemini suit was a mesh that prevented the ballooning problem experienced during the Russian spacewalk.
I feel like $1 million.
The first American spacewalk went so well that NASA assumed working in space presented few obstacles. White's joyride in space gave no indication of the difficulties that lay ahead. The Gemini program had a number of goals, and in December 1965, Gemini 6A and Gemini 7 achieved 2 of them: rendezvous and long-duration flight. The crew of Gemini 7 remained in orbit for 14 days. Mission planners knew that staying in a spacesuit for 2 weeks would be a challenge, so a new version of the G3C spacesuit, called the G5C, was worn by the Gemini 7 astronauts. It replaced the pressure helmet with a zippered hood, and Frank Borman and Jim Lovell became the first people to remove their spacesuits in flight. New technologies were being pioneered in the Gemini spacecraft, and problems with the new systems often meant Gemini flights were only partially successful. The capsule had to be capable of far more complex maneuvers than its predecessor, and longer duration missions required fuel cell technology for electric power. In March 1966, Gemini 8 had successfully rendezvoused and then docked with the target vehicle. But a thruster problem sent the linked craft into a spin. The mission was immediately terminated. The scheduled spacewalk did not take place, and the craft landed in the Pacific, half a world away from the planned landing area. 3 months later, Gemini 9 could not dock because its target vehicle's fairing had not been jettisoned. The scheduled spacewalk went disastrously wrong. When Gene Cernan inflated his suit, it did not want to bend. Exhaustion and a fogging space helmet saw Cernan called back inside. He was overheating. Training for a spacewalk was limited to brief periods of weightlessness in an aircraft, or being suspended in a special jig that moved via an air suspension system across a smooth floor. Neither provided anything like the real thing. Engineers had realized that the current generation of spacesuit worked well sitting in a spacecraft, but when doing strenuous work, its air cooling system was inadequate. New designs were already in train. The next 2 Gemini flights both failed to demonstrate that an astronaut in a spacesuit could do meaningful work in space. Before the final Gemini flight, a new training simulation was tried. A mock-up of the Gemini craft docked to an Agena target vehicle was built in the McDonough School indoor pool. An approximation of the true weightless environment, it allowed astronaut Buzz Aldrin to train for extended periods. Handholds were fitted to the outside of the spacecraft, and the extravehicular work assignments on Gemini 12 were a complete success. It gave NASA planners the confidence to move to the Apollo program and the final stages in America's progress to its moon landing. By 1966, it was apparent that Apollo was well behind schedule. The first manned flight of the program had been delayed by almost a year because of developmental problems with the Apollo spacecraft. NASA was rushing to meet the 1969 moon landing deadline set by President Kennedy, and privately some in the astronaut corps felt that the hurry was not good for the development of a new capsule. NASA had flagged changes to later models of the spacecraft, but the early Block 1 version would still carry a crew in the first manned mission to test systems in Earth orbit. A new spacesuit was being developed for use on the later moon missions, but it would not be ready for Apollo 1, whose astronauts, Gus Grissom, Ed White, and Roger Chaffee, would wear a slightly different version of the Gemini GC-4 suit. All American spacecraft had been pressurized with pure oxygen. This had weight-saving benefits, and by exclusion of nitrogen found in natural air, the danger of bubbles forming in the bloodstream during rapid decompression was eliminated. Though the pure oxygen environment presented a fire danger, nobody had thought to check the real risks. In January 1967, less than a month before the scheduled launch date, the Apollo 1 crew were in their capsule under simulated launch conditions, with the craft being tested under its own power. A spark triggered a fire, and in seconds the crew were dead. The inquiry into the fire found the astronauts had died of asphyxiation from carbon monoxide. Both the spacesuits and the cabin made extensive use of combustible materials. For the program to continue, everything would have to be redesigned. Research into the problems associated with a spacesuit that could be used on the moon had been going on since 1962. The new suit had to be rugged. Designers were still not sure what the lunar surface would present. All previous suits had been fed with oxygen and power from an external source. The moon suit had to be self-contained, and the backpack supplying life support presented problems. The backpack's dimensions and weight were determined by extensive testing, and designers of the life support, battery and communication systems worked within strict parameters. After the Apollo 1 tragedy, flammable components had been removed, and an outer layer of beta cloth, of woven silica fiber coated with Teflon, was added. Many different ways of simulating the moon's 1/6 gravity were trialed. Finally, the A7L suit emerged. Beneath the outer layer, a tight-fitting suit with elbow, wrist, and knee joints of a bellows-like structure that maintained equal volume when bent, allowed freedom of movement absent in previous suits. Beneath the pressure suit, a light open-weave layer was networked with fine tubes circulating cooling water. This carried away excess body heat that earlier air-cooled suits had not coped with. The pressure suit and the outer protective layer were joined together, with the inner cooling garment remaining separate. On Earth, the whole suit weighed 35 kilograms, with the backpack a further 60 kilograms. It was the A7L that went to the moon with the first 3 successful Apollo lunar missions, and it performed flawlessly. It continued to evolve as subsequent missions became more demanding. The moon suit was robust, and Apollo astronauts had complete confidence in it. No lunar mission ever had a problem with the spacesuit.
We have maintenance stuff.
With the arrival of the space shuttle, NASA was expecting to do serious work in orbit, and it needed a new spacesuit. The Extravehicular Mobility Unit, or EMU, is a direct descendant of the Apollo A7L. Its main difference is the rigid upper torso. Because they are used in a weightless environment, the new suits could be heavier than the Apollo suit, which operated in lunar gravity. The EMU is not custom-tailored for each user. Components are made in a range of sizes and are interchangeable. Parts are intended to have a useful life of around 15 years. With the shuttle, NASA envisioned servicing satellites in low Earth orbit, but first it had to learn how to do simple tasks. New technologies were combined with the spacesuit. In 1984, astronaut Bruce McCandless, using the Manned Maneuvering Unit, flew independently beside the Space Shuttle Challenger. After 4 hours, he returned safely. The MMU was used for satellite recovery on 2 subsequent occasions, with mixed results. After the Challenger disaster, NASA reviewed all aspects of safety, and the MMU was retired as too risky. A simpler technique emerged. With foot restraints on the shuttle's robotic arm, astronauts could be moved accurately to a site and have a stable work platform. In 1990, the Hubble Space Telescope was launched. Unlike other satellites, Hubble was designed to be visited by the Space Shuttle for regular maintenance and upgrades. Over a 16-year span, there were 5 servicing missions to the telescope, the first being to fix an error in its manufacture.
Is a game-ending activity.
Each servicing mission called for long and complex spacewalks. The EVAs were all thoroughly rehearsed in NASA's Neutral Buoyancy Laboratory. The astronauts are weighted so that they neither rise nor sink, and all the large components that they handle are similarly neutral. Astronauts still have the perception of up and down in neutral buoyancy, unlike in weightlessness. In 1998, work commenced on the International Space Station, a collaboration between the US, Russia, Europe, Japan, and Canada. This was the type of project for which the Space Shuttle had been designed, and the expertise that NASA's astronaut corps had gained was to be put to use for on-orbit construction. As the space station grew, the EMU spacesuit was refined. Increased battery capacity was added so that small heaters in the gloves could keep astronauts' fingers warm during passages through the Earth's shadow. A new safety system was added to the EMU suits. Called SAFER, the Simplified Maneuvering System is designed for emergencies in the rare event that a spacewalker becomes untethered from the space station. It was first tested in 1994, but it has never been used for an actual emergency. With the completion of the ISS in 2011, the Space Shuttle was retired. This meant sole access to the orbiting laboratory was via the Russian Soyuz spacecraft. Cosmonauts and astronauts wear the Russian Sokol flight suit during trips to and from orbit. For maintenance and repair sorties outside the ISS, crew will wear either the EMU or the Russian Orlan spacesuit. Many of the Europeans on board have training in the use of both. The Orlan spacesuit is very practical, designed to be serviced on the space station. It has a rigid torso, with the helmet and visor joined to the suit, and access is via a rear hatch. Cosmonauts wear a water-cooled undergarment similar to the American suit. Unlike the American suit, the Orlan can be put on in just 5 minutes. In the MKS, the latest version of the Orlan, a cosmonaut can safely remain outside for 7 hours. And finally, NASA is working on a new generation suit to meet its future needs. Called the PXS for Prototype Exploration Suit, it also features a rear entry hatch. The PXS has a more advanced life support system and is lighter. A different version, called the Z2, is being developed for use on the surface of Mars. It allows a greater range of movement, and its life support system will take less time to recharge, although neither suit has yet been used in conjunction with its life support backpack.